let's get started. My name is Bryce Adelstein Lelbach, and I have worked on programming languages and compilers for well over a decade now. And I have served as the chair for the Standard C++ Committee's Library Design Group, which decides what things are going to go in the standard library and what the shape of those things will be. And I am a principal architect at NVIDIA. This is a lovely NVIDIA holiday sweater. And there I drive our strategy for programming models, compilers, and libraries, mostly for HPC, primarily in C++, and now in Python. But today, we're going to talk about C++. I want to teach you about the C++ execution model. So this model is what makes C++ portable today. It's not about how many bits you have in a byte. That's sort of a settled question, or 2's complement, sort of a settled question. And we basically have two microarchitectures. But we have a great divergence in platforms' concurrency capabilities. And so C++ defines a standard for multi-threaded execution that is broad enough that any platform can implement it, from the smallest DSPs to server CPUs and GPUs to even more exotic accelerators like TPUs or some sorts of ASICs. So to understand the C++ execution model, we're going to actually read through some parts of the C++ standard itself slowly, don't worry. And we'll discover some of the core concepts and the rules of the execution model, and we'll see how it works in the real world and some of the consequences of those rules. So at the heart of the C++ execution model is the C++ abstract machine. And someone gave a great talk about some of the details of how hardware works this morning, and they pointed out the fact that there is no actual C++ abstract machine. Like, what is this thing? Well, the C++ abstract machine is just this portable abstraction of your operating system, kernel, and hardware. And it's just an intermediary, a conceptual intermediary between your C++ program and the system that it is run on. The C++ abstract machine, it isn't an actual piece of software. C++ doesn't have a virtual machine like languages like Java or C#. This is just an idea. It's just a notion. It's just some theory. That's all that the abstract machine is. So the idea is that you write portable code, and then you want to deploy it on a diverse range of concrete systems, where a system is a combination of hardware, operating system, and compiler. And so your code gets mapped onto the semantics of the abstract machine. And then many different platforms implement those semantics. So C++ programs describe operations that are performed on this abstract machine. And C++ implementations define the characteristics of their implementation of the abstract machine. And then they translate operations on the abstract machine into operations on the system. Now, implementations only have to behave as if they implement those required semantics. So an implementation is free to disregard any requirement as long as the result is as if the requirement had been obeyed, as far as can be determined from the observable, valid behavior of the program. So for example, an implementation doesn't need to evaluate an expression or store an object if it can deduce that that entity is not used, and that getting rid of it will have no observable side effects. So this is called the as-if rule. And this is the thing that we hand-wave to a lot when we try to make abstractions zero cost in C++. It's like, yeah, I know it should do all those things in terms of the abstract machine, but we can hand-wave an as-if, and the compiler will optimize that away. So the abstract machine's model is actually pretty simple. It is a collection of threads executing operations on objects that reside in a flat global storage. So there's two key components here: storage and threads. So the storage is flat there is no notion of hierarchy in the C++ abstract machine. There's no notion of caches, etc., or any form of hierarchical memory. Objects just reside in some flat storage at a single memory location. Every byte has a unique address, and no 2 bytes have the same address. Now, some objects may not have a unique memory location. For example, eligible empty base classes, or objects that are marked with no unique address. And an implementation is allowed to store 2 objects at the same machine address, or not store an object at all. For example, let's say that you have an int, and you never take the address of it, and you never modify it, and its value is a literal. The implementation doesn't need to store it, because under the as-if rule, you can't observe if it's not being stored. It's as if it's in that storage. Like, conceptually, it is in the global storage of the abstract machine, but in the implementation in the real world of that abstract machine, it's not actually stored in memory. So an object in the C++ model cannot have more than 1 memory location. If an object could have 2 addresses, a bunch of weird things would break. For example, we would no longer be able to compare object addresses to check for object equality. Consider this self-assignment check here. Now, this is just one example. There's many far-reaching consequences of these aspects of the object model. Compilers can even optimize based upon guarantees like this. And so if we broke those guarantees, then that would be problematic, because then our code would be ill-formed, because the compiler would optimize it in ways that would break our semantics. Every thread in a program can potentially access every object and function in a program. This means that the C++'s view of memory is global, that there's no such thing as memory that is private to a particular thread. Your thread, if it's able to get its hands on the address of an object, it's allowed to access that object. So now let's look at some example memory systems and evaluate whether they can implement the C++ abstract machine. So does this system meet the constraints of the abstract machine? We've got 2 different processing units that have shared memory, like 2 different CPUs in a multi-socket system, and they have some shared caches. And we've got a single process that's running on this system. This is fine. All of the objects are going to be accessible by all of the threads. So we're good here. But how about this system, where we have 2 different processes? Well, this is outside of the scope of the C++ abstract machine, because we have memory that is private to some of these processes. And so this is outside of what standard C++ can handle. So this means that things like shared memory IPC or distributed programming via something like MPI or RDMA, that's outside of the standard C++ model. Now, what if we have a system like this with 2 types of processors, each with its own distinct memory that is inaccessible to the other? So this still violates the C++ storage model. We don't have objects, we can't have objects that are not globally accessible. So for example, a heterogeneous CPU and GPU system needs to have unified memory to support standard C++. The GPU threads need to be able to access the memory of the CPU threads. So now let's move on to the other piece of this, to the threads part. Threads are the primary agent of action in C++. They're the things that actually do everything. So a thread of execution is a single flow of control in a program which evaluates a function call. Threads may run concurrently. So that's all that threads are. They just evaluate a function. So there's the main thread of execution in a program, which evaluates the main function. Stood thread and stood J thread also create a thread of execution, which evaluates the invocable object that is passed to them. Now let's talk a little bit about how initialization interacts with threads. So variables with static storage duration are initialized as a consequence of program initiation. So static objects are going to be constructed before main and destroyed after main. Variables with thread storage duration, so thread local, are initialized as a consequence of thread execution. So they're created before the thread starts, and they're destroyed after the thread finishes execution. So threads evaluate a function call. What does it mean to evaluate a function call? To understand what evaluating a function call means, we first have to understand what evaluation means. And to understand evaluation, we first must understand what expressions are, because that's what evaluation operates on. So an expression is a sequence of operators and operands that specifies a computation, like a function call or, a plus b, etc. Sub-expressions are part of a larger expression. So for example, here we have a statement that declares and initializes a variable of type t, contains a number of sub-expressions, a call to the constructor of t, an indirect function call, a dereference designating the function body being called, and the expressions that produce the arguments to the function call. Full expressions are top-level expressions. They're just defined as any expression that is not a sub-expression. So full expressions may include sub-expressions that are not lexically part of the expression, such as the end of a scope, which we'll call destructors, or a function call, which may have default parameters. And those default parameters, the expression for those default parameters, will be evaluated from the place where it's called. Such implicit calls are considered expressions for the purpose of the execution model. Evaluation of an expression includes value computations and the initiation of side effects, but not necessarily the completion of those side effects. This is very important. So side effects are things that change the environment. Reading a volatile object or modifying any object, calling a library I/O function, or calling a function that does any of the above things. So here, the side effect of A equals A plus B, it's modifying an object. The side effect of cout of A times A, that is calling a library I/O function. And the side effects of foo of A plus B, that would be, we don't know because we don't know what foo looks like, but it would be whatever side effects are associated with foo. If we go back to this, we said that evaluation of an expression includes the value computations and the initiation of the side effects. Probably, at some point in your career, you have had a time where you've couted something, and it hasn't printed to the screen when you've wanted it to, and then you've gone and added something like a stood flush or a stood indel to the end. This is a perfect example of how side effects may not be completed by the time that an expression finishes evaluation. Now, this is a little bit more obvious for I/O, but this is also true for something like writing to memory, and that's a little bit less intuitive. So the value computations are pure and have no observable effect. The completion of the execution of an evaluation does not imply completion of its side effects. So we just talked about this. When we complete evaluating this expression, it doesn't necessarily mean that the I/O has happened yet. Given any two evaluations, A and B, within the same thread of execution, if A is sequenced before B, then the execution of A shall precede the execution of B. So this is the first of the three key ordering relationships in C++. It's called sequenced before. So the sequenced before relationship is asymmetric. If A is sequenced before B, that means that B is not sequenced before A. It is also transitive. If A is sequenced before B and B is sequenced before C, then A is sequenced before C. So each full expression is sequenced before the next full expression in program order. So here, A is sequenced before B. It's basically just saying that within a thread, things happen. Things are sequenced in the order that they appear within a thread. So if A and B are indeterminately sequenced, then either A is sequenced before B or B is sequenced before A, but it is unspecified which. So that means that A and B are not interleaved. I'll take questions at the end. You can write down the slide numbers if you got a question. If A and B are unsequenced, then A is not sequenced before B, and B is not sequenced before A. So that suggests that the evaluation of A and B might be interleaved. It might actually occur at the same time. So let's look at this with an example. So if A is sequenced before B, then A executes before B. This is serial execution, which is how our minds typically tend to think. If A and B are indeterminately sequenced, then one of them executes before the other, but we don't know which. So this is thread parallel execution. And if A and B are unsequenced, then their execution may potentially overlap. And so this could occur when we're doing vector parallelism, when we're doing SIMD. So let's look at an example using the C++17 execution policies. So here we're using the std execution seek policy, which guarantees that each iteration is sequenced before the next within the same thread. Now, if we instead use the par execution policy, the iterations may be executed in parallel by multiple threads, but they will not be interleaved. If we use std execution on seek instead, it'll all run within one thread, but the iterations of the loop may be interleaved. And so your compiler could go and reorder them like this, and then could replace them with vector instructions. All right, so what about statements? I like to think of statements as just being compositions of expressions insofar as the C++ execution model is concerned. It's all just expressions. So statement 0 here, whatever it would be, is going to be sequenced before statement 1. The condition of an if statement is sequenced before the body of that if statement. And the condition of a while loop is sequenced before each evaluation of the body. And likewise for for loops. So now let's look at how C++ operators are actually evaluated. So again, the value computations, but not the side effects, of an operator are sequenced before the value computations, but not the side effects, of its operands. So the operand expressions to the following operators are sequenced left to right. So you evaluate the left-hand side first. But for assignment things, you evaluate the right-hand side first. Whatever you're going to be assigning from before you evaluate the source. Now, what about the most important operator, calling a function? Well, now that we've understand everything else about expression evaluation, we can finally dive into what function evaluation is. Now, remember, we said that all that the thread does is evaluate a function. So if we understand what evaluating a function is, then we'll understand what threads actually do. So when calling a function, every evaluation within the function and every evaluation not within the function are indeterminately sequenced. So the compiler is not allowed to mix up your function with other functions and interleave the bits of it with other functions, even in the case where it's inlined. The expression designating the function is sequenced before the argument expressions. This kind of makes sense. Figure out what you're calling before you figure out what you're going to be calling it with. Each argument expression is indeterminately sequenced with all other argument expressions. And every expression in the body of a function is sequenced after the expression designating the function and every argument expression of the function. Again, this one just makes sense. Before you can start evaluating the body of a function, you need to evaluate all of the arguments, and you need to evaluate where you're getting the function from. So let's look at an example. So here we've got a function b, which takes 2 parameters and has a body e. We've got a call to another function g, which takes 3 parameters, the expression a, an expression containing an indirect call through a function pointer to b, and then the expression f. And the call to b takes 2 parameters, the expressions c and d. So the expression designating the function being called, the dereference of b pointer here, is sequenced before the argument expressions to that function call, which is c and d here. Again, this logically makes sense. You want to figure out what you're calling before you figure out what arguments you're calling it with. The arguments to a function call are sequenced before the body of the function call. And again, this just makes sense. We have to evaluate the arguments before we start evaluating the function. All of the arguments to a function call are indeterminately sequenced. So C and D are indeterminately sequenced here. Every evaluation within a function, like E here, and every evaluation not within the function, like A and F here, are indeterminately sequenced. So again, that is that we don't interleave observable stuff from outside of a function within the function, even when we're like inlining it and then doing a bunch of optimizations. Likewise, AF and the result of the B call are indeterminately sequenced. And then finally, A through F are all sequenced before whatever the body of G is. So together, these 4 rules describe the sequencing of our function calls, which ultimately describes the sequencing of our entire program. As we can think of our program as just being a collection of function call evaluations, starting with the evaluation of the main function. So now we've established how things are ordered within a thread. And now we have to talk about how operations are ordered across threads. And that is with synchronizes with. So a library operation A may synchronize with other library operations B performed by other threads. This is not symmetric, so A synchronizes with B does not imply that B synchronizes with A. It may be the case that that happens, and there's a few places where it does, but it is by definition a one-way relation. There are many standard library operations that achieve synchronizes with, such as atomic acquire and release from a store to a load, mutex lock and unlock, from the unlocks to all subsequent locks, thread create and join, barrier arrive and wait, and parallel algorithm fork and join from the caller to, or from the work being done to the caller at the end. So synchronizes with is a runtime relationship. You only have it if the operation observes the result. So imagine that we have 2 threads communicating data with an atomic flag. The first thread does a store release stores to the data and then does an atomic store release to the flag. If the load on the right sees a value of 1, then we have a synchronizes with relationship, but only if its load acquire here sees that value of 1. If it sees any other value, then we do not have a synchronizes with relationship. So that second thread, it does a load acquire of the flag, and then it loads the data if the flag was set. And if the flag is set, we have this relationship. But otherwise, we do not. So if the load doesn't see the store of true, then we don't have a synchronizes with relationship in either direction. You cannot synchronize from a load to a store, only from a store to the load, to a load. So the store has to happen first, starting the synchronizes with relationship, and then the load has to see it, and then you've achieved synchronizes with. So another example with mutex unlock operations will synchronize with all subsequent mutex lock operations. So next, we have the most important ordering relationship in C++, which is happens before. So given any two evaluations, x and y, if x happens before y, then x is sequenced before y, or x synchronizes with y, or for some evaluation z, x happens before z, and z happens before y. So just a transitive property. So this happens before ordering describes arbitrary concatenations of sequences of sequenced before, which is the ordering within a thread, and synchronizes with, which is the ordering between threads. So all operations within a thread that are sequenced before a synchronized with will be observable to the other threads participating in the synchronizes with. So let's look at that example that we just saw. Here, the left thread stores non-atomically to data, and then it does an atomic store release to the flag. The store to data is sequenced before the atomic store to the flag. So the data store happens before the flag store. Likewise, the atomic flag load on the right is sequenced before, and thus happens before, the non-atomic data load. Now, if the flag load on the right sees the flag store of true, then you've got synchronizes with between the flag store and the flag load. And so then that means that the data store happens before the flag store, and the flag store happens before the flag load, and the flag load happens before the data load. So therefore, transitively, the data store happens before the data load, even though they're both non-atomic. And thus, we've got a safe program. Now, happens before doesn't mean that something temporally happened before something else. Generally speaking, if you were able to write a program that was to witness this disconnect, then your program would have undefined behavior. So for example, consider the function foo here. It sets x to y plus 1, and then it sets y to 1. The assignment to x is sequenced before the assignment to y. But if you look at the assembly for this code on some compilers, you'll see that the assignment to y may actually be interleaved with the assignment to x. First, we load y into a register, and then we store 1 to y, and then we add 1 to the value in the register, and finally, we store that value to x. So the ordering here is not what the C++ abstract machine says it is, but it's not observable. It's fine because these are just ints. There's no side effects here other than modifying the object, and the compiler can prove that this is safe. Now, if you threw in a function call to a function in another translation unit here that just read y or something, or took the address of y, then the compiler wouldn't do this, because it would be like, I don't know what that function does. It might observe that I'm doing things here. So again, happens before doesn't mean that something temporally happened before. Doesn't mean that if you've got x happened before y, that doesn't mean that x actually occurred in time before y. It's about the observable behavior, not the actual behavior. Now, a well-defined program is guaranteed to observe things in the happens before ordering, even if that's not what actually happens under the hood. And likewise, happening before in time doesn't mean that you have the happens before relationship. Just because X occurred in time before Y does not imply that X happens before Y. In one particular execution of your program, or even in most executions of your program, X may occur in time before Y, but that is no guarantee that that you're going to get the ordering that you want. It may happen to work, but that doesn't mean that you have a happens before relationship. Now, if you rely on ordering that is not guaranteed by happens before, then you'll have a data race. So data races start off with conflicting operations. So two expression evaluations conflict if one of them modifies a memory location and the other one reads or modifies the same memory location. A data race occurs when you have two conflicting operations performed by different threads, at least one of which is not atomic, and neither happens before the other. Now, any such data race will result in undefined behavior. So consider this program here. We're communicating an int between two threads. This int is initialized to 0. So the producer thread writes 42 to data, and the consumer thread reads from data and then prints it. We have two threads performing conflicting operations, at least one of which is non-atomic, and there's no happens before relationship. And so we have a data race, and thus we have undefined behavior. And that means the program could print 0, it could print 42, it could print another random integer value, it could print, an infinitely long string, it could just print forever, and it could crash, like anything could happen. Now, if we introduce a synchronization primitive, such as a semaphore, then we can get a happens before relationship. So here, the release in producer will synchronize with the acquire in consumer. And so the store to data happens before the release, and the acquire happens before the load. So therefore, the store to data happens before the load of data. And then we know that this program will print 42. We could also use an atomic flag and acquire release semantics to get the same happens before relationship. So here we're using atomic's wait interface to block until we observe the producer's store. But if we used relaxed loads and stores for the flag, then we won't get a happens before relationship between the store and the load. Relaxed loads and stores are not synchronization operations. They can only be used for communicating information about that particular atomic object. They give you no guarantees about ordering of operations of non-atomic things in other threads. And so we would be back to undefined behavior here if we used memory order relaxed. Now, if we instead make the data atomic itself, and we do a relaxed store and a relaxed load, then we'll have a well-defined program, but it'll be an interesting one. We don't have any happens before relationships here between the threads, but all of our conflicting operations are atomic, so we do not have a data race. So what you'll get here is you'll get a well-defined program that will either print 0 or will print 42. It'll be one of those two things. It is guaranteed. You don't get any promises about which of those two things, but it will not crash. It will not print out other values. It will not, launch the missiles or whatever. It'll do one of those two. It'll execute one of the two valid orderings. So now that we understand threads and how they evaluate expressions and how those evaluations are ordered and what data races are, the final thing we must learn is what guarantees we get when threads block or wait on something. So we start off with the idea of execution steps. So the evaluations that are executed by threads are delineated by execution steps. So an execution step is the termination of the thread and access of a volatile object the completion of a library I/O function, a synchronization operation, or an atomic operation. And the completion of an atomic operation could include spurious failures. Now, blocking is waiting for a condition to be satisfied before continuing execution. So, blocking library functions are considered to continuously execute execution steps while waiting for their condition to be satisfied. Remember, what execution steps do, it's like either you read a volatile, you do some atomic, or you do a synchronization function. So the idea is that one of those things will eventually satisfy your condition because you're communicating with other threads. So a thread of execution makes progress when it performs an execution step or a lock-free execution that does not complete because other threads are making progress. So some atomic operations can fail spuriously due to interference from other threads, and implementations are encouraged but not required to prevent spurious failures from indefinitely delaying progress. So for example, on load, locked, and store conditional architectures such as ARM, another thread may repeatedly steal your desired cache line for unrelated purposes in between the load locked and the store conditional instruction. And on those architectures, weak compare and exchange operations may fail spuriously. So even when the atomic's object's value is equal to the expected value, it may fail to complete successfully. So forward progress essentially just guarantees that something observable will eventually happen. That if I'm blocking, that I will eventually observe some condition change that will allow me to move closer to not blocking. Now, implementations may assume that all threads will eventually perform an execution step. So this has the implication that things like infinite loops that have no observable side effects are undefined behavior and thus can be deleted. Now, finally, we can talk about the forward progress guarantees that threads might provide. And there's 3 different classes of forward progress guarantees. Concurrent forward progress gives you a promise that the thread will make progress regardless of whether other threads are making progress. So examples of concurrent forward progress include preemptive operating system scheduling algorithms such as fair share and round robin. So if you've got an OS thread and your OS is configured to use one of those algorithms, then you're good. Or an unbounded thread pool that will add new operating system threads to the pool as needed to make progress. So parallel forward progress gives us the promise that once the thread has executed its first execution step, then the thread is guaranteed to make progress. So basically, once it starts running, you're guaranteed that it will complete. But if it hasn't started running yet, you have no such guarantee. So examples of parallel forward progress would include tasking frameworks where tasks cannot be interrupted, such as bounded thread pools, so any framework where a task will run to completion, or threads on NVIDIA GPUs. Then finally, we have weakly parallel forward progress, which is a nice name for no forward progress guarantee. Weakly parallel forward progress, the thread's not guaranteed to make progress. Great naming. It's his fault. Examples of weakly parallel forward progress include non-preemptive operating system thread scheduling or tasking frameworks that support task suspension, such as fibers. Because your thing could start running, and then it could be suspended, and then it could never start running again. So what guarantees do we get from the main thread? Well, this is actually implementation defined. And it's the same for std thread. And on most popular platforms with an operating system, you're usually going to get concurrent forward progress guarantee from both your main thread and from std thread. On embedded platforms and platforms that have no threads, though, it may be weaker. Because if you have no threads, I have no way of providing concurrent forward progress. So at the end of the day, concurrent forward progress is just a promise that, like, you're going to run on, this thread's going to run on some actual dedicated hardware. And it has a guarantee that, like, when it's ready to run, that there will be hardware resources available for it. But on some platforms, we may not have that guarantee, like on some embedded platform with no threads, or some embedded platform where, like, a non-maskable interrupt could come in and you could just be, indefinitely paused while something else happens. So when library functions block, and also your code, you need to ensure that progress is being made. In particular, you need to do this in the face of the potential that you might be blocking on a thread that has weaker forward progress guarantees than your current thread does. So if I have a concurrent forward progress guarantee thread that's blocking on a weakly parallel thread, that could be a problem, because I could end up blocking forever, because I have no guarantee that that weakly parallel thread will actually make progress. So more specifically, when a thread P boost blocks on a set S of other threads, the forward progress guarantees of at least one of the threads in S are, or at least one of the threads in the S is chosen and is temporarily upgraded to P's forward progress guarantee. And you repeat this until the blocking condition is satisfied. So the idea here is that if you're blocking on someone, you need to proactively do something to preserve your forward progress guarantee while you're blocking. And that usually means you need to donate your stronger forward progress guarantee, which means donating your execution resources to whatever you're blocking on. So boost blocking ensures that your children threads make progress. That's something that you're waiting on makes progress. But it doesn't say anything about your siblings, so other threads that you're synchronizing with your neighbors. It does not protect you from inhibiting the forward progress of weaker threads when you're using synchronization primitives. So let's work through this with an example. So here's a simple implementation of a thread pool with a fixed number of workers. So we have a queue of callables, and we have a mutex. Execute async enqueues a callable, and then returns a shared pointer to an atomic bool, which is just a poor man's future or sender. And that will be set to true once the work item has been executed. We do that in the body of the callable. And then we have a wait function that takes one of the tokens returned by execute async and waits for it to be ready. So this is a bounded thread pool, and so it will have parallel forward progress. It's not going to add new operating system threads as it needs to. Just copy twice. Each thread in the thread pool will execute process items, which is going to contain this loop here. And so this loop is going to call try-pop, which will lock the mutex. And then it will check whether there is work in the queue, and if so, then it'll pop a task from the queue, and then it'll execute that task. And the tasks in the queue, we can think of these as being threads of execution with parallel forward progress. So once they start executing, they will run to completion on the worker thread, assuming that the worker thread has concurrent forward progress itself, which is usually going to be the case for stood threads, as we said. So now suppose that one of the tasks that we enqueue in this thread pool wants to parallelize its work. And so it spawns some children tasks to process part of the work in parallel. And then it performs part of the work itself. And then finally, it waits for the children to complete. So what happens if the thread pool has only one worker serving it? Then the worker will start executing the outer task, which is going to enqueue the children, and then blocks pending their completion. The children, though, they're never going to complete because there is no execution resource for them to execute on. We have one thread, and that one thread is currently blocking, waiting for the children to complete. And so it is necessary for our wait function to boost block, to pull tasks from the work queue and execute them until the blocking condition is satisfied. So to fix this, we have to go into wait, and we need to modify it. So any thread that calls wait needs to ensure that the work it's waiting on will make forward progress. And the simplest way to do that is just to make sure that the entire queue makes forward progress. And so instead of unconditionally waiting on the token for our task, we can check the token in a loop while also processing work items ourselves. And this donates the calling thread's progress to the work that it is blocking on. So with this change, even if we have just one thread in the pool, this code will be fine, because when we hit the waits here, instead of blocking forever, we'll eventually execute the child task ourselves in the thread executing the parent task. And so this is what we do inside of standard library synchronization functions that have to block to ensure that we make forward progress in the face of a variety of different types of tasks, like things in thread pools or things on GPUs, et cetera. And if you're writing code like this, you also need to write it in this way. So we've reached the end of our journey here. And so to summarize in a slide, in the C++ execution model, we have threads that evaluate expressions that access and modify objects in flat storage. The evaluations within a thread are driven by the sequenced before relationship. Interactions between threads is driven by the synchronizes with relationship. And the happens before relationship ties the two together. It gives you arbitrary concatenations of sequenced before and synchronizes with, which allows you to reason about ordering both within threads and across threads. And forward progress gives us a promise of eventual termination. So I have made a number of simplifications and ignored some corner cases. So we've just completely ignored memory order consume. We're looking at the wording before some of the fixes to memory order consume, because it's a lot simpler to understand the model this way, and nobody actually uses memory order consume, so you don't have to worry about it. It's the same basic principles. There's also signal handlers, which we've left aside, which can introduce some complications with forward progress and also with memory ordering. If you want to learn more about parallel programming and algorithm design, my buddy Connor and I have a podcast, ADSP, Algorithms plus Data Structures equals Programs, available on all streaming platforms. You can go subscribe now. And I've given a lot of conference talks this year on these general topics. It's all the little pictures where we were in the Galapagos and my girlfriend took all the little pictures. This is a baby Nazca booby, so it's a little seabird. They're very cute. We were like 2 feet away from them. It's really cool. So thank you all for your time and attention. I will now take your questions.
Thank you. Just to make sure I got this right, there's thread local storage, but in the execution model, it seems nothing like that exists. So if I give the pointer to thread local storage to another thread,
it's accessible.
Can
yeah.
just access it.
So if you access the object, the way that thread local storage works on a lot of platforms is with like a segment register. And in the terms of C++, and by the segment register, I mean like there's this little magic register that's set differently on each thread, and then you add that segment register to some address, and that gives you an offset into a table, and that's how thread local storage is made fast. In terms of C++, when you access a thread local object, you're getting the object in your thread, and so you might think, like, how do I access? I can't access the thread local objects in other threads, but that memory is just in some array somewhere. If you got the address to it, you could. So if you have one thread and the thread takes the address of its thread local and passes it to another thread, that's completely fine. You can access the other thread's thread local through that address. It's just that if I'm in a thread, I don't have any way to get that address. Well, I mean, if you want to go to UB, it's likely offset from your current address, the address of your current thread local. But yeah, it is globally accessible.
Okay, thanks.
So there are platforms like NVIDIA GPUs where this is not the case, where we have, well, for thread local it would be, but we have other types of thread local storage that is not accessible to other threads. And in fact, on GPUs, your stack variables that are just local variables in the stack are not accessible to other threads. If you take the address of something on your stack and you pass it to another thread on a GPU, that's not going to be a valid address for you to use because we swizzle the stack. So we do some magic like reordering of the stack under the hood. And so the address of a local in one thread is not going to be good in another thread. And so in that sense, a GPU may not implement to 100% the semantics of standard C++.
Hello, awesome presentation, thanks. I have a couple of questions from our audience online. So the first one is from Marcus Verle, who asks, you described the abstract machine as having threads. Does this mean that a C++ program running on an STM32 bare metal without operating system may be running in cooperative multitasking via DAF's device is not inside the realm of C++ standard?
I don't know enough about that particular platform to be able to say, but as we said before, there's no guarantee about the forward progress that you get out of the main thread or std thread. So, and okay, if you look at if you consider a thread with weekly parallel forward progress, which is just a thread that makes no guarantees that it makes any forward progress, like every chip that's a Turing complete machine has that. It's just saying you can evaluate code. I can execute code. It's not saying that there's other threads there, but a thread of execution can exist in a world without concurrency. So every processor that you can think of has at least one thread of execution. It may not make any forward progress guarantees. But yeah, I don't think that that platform is not able to implement standard C++. It may just not make strong guarantees about what the main thread's forward progress is.
Sure, thanks. Another question from Thomas Kleiss. I've been wondering for a long time how resilient function calls are as sequence points if the linker/compiler potentially optimizes these calls out or removes the calls. Is a valid C++ compiler still required to make sure that everything happens as with the calls still present?
Sequence points are no longer a thing. That was like a that was a pre-execution model and memory model thing. This whole talk explains how the ordering guarantees you get. You don't get. I mean, you get the ordering that we described for function call evaluation, which is that stuff within the function won't be interleaved with stuff outside of the function. But the sequence point model is no longer around. And so if you're asking that sort of question, you probably want to go take a look at what the current multi-threaded execution model looks like, because it's a bit different from sequence points, and sequence points was not really a model that could properly support concurrency.
Sure. One last question from the online audience, from Hani Sukasan. Many new terminology I learned from this talk. Thanks, Bryce. If I have to explore more on this talk, do you suggest any books or talks?
Yeah, it's actually the second time in 2 days I've gotten that question. And rarely I do have book recommendations because I usually don't read a lot of programming books. But Anthony Williams writes a lot of books on concurrency, and he's somebody I trust. So pick up one of his books. There's also a lot of talks you can watch on this. So I've given a lot of talks on this topic. I gave a talk on the C++ 20 synchronization library. And my talk on C++ standard parallelism covers a lot of this. Any talks that Olivier Giraud, who's the chair of the C++ concurrency committee, has given will cover, some amounts of this. Fedor Pikas also gives good talks on this. But if you're looking for a book, Anthony Williams' books are probably the ones I would go with.
Sure, thank you.
Yep.
Bryce, a minor thing. Can you go back to slide 112, please?
I can. Yeah.
I think here we are missing the call to notify one.
Yeah, that's because the weight should be. Yeah, we are missing a call to notify.
Notify
Yeah,
one or
yeah,
notify
there should be a call
all.
to notify there. Yeah.
Okay.
Any other questions? Okay, cool. Come find me later. I'll be here till Sunday.